Welcome back to another explainer. Today we are unpacking a really exciting, brand new framework out of Duke and NYC called PARSE. If you follow generative AI at all, you already know that making these massive models run efficiently, well, it's basically the engineering hurdle of our time. So we are going to explore exactly how this newly published framework dramatically speeds up large language models.
At the heart of this whole discussion is one fundamental question. How do we make LLMs faster without breaking them? We are scaling generative AI to totally unprecedented heights, with models boasting hundreds of billions of parameters. And we desperately need them to generate text faster for real-world applications, but we absolutely cannot afford to sacrifice their reasoning accuracy just to get that speed. It's kind of been this stubborn tug-of-war.
Okay, let's dive into this. Here is our roadmap for today. First, we will look at the LLM speed problem, then the speculation trade-off. After that, we will introduce PARSE, break down exactly how it works, and finally, look at those speed-up results.
All right, kicking things off with Section 1, the LLM speed problem.
So the root of the issue here is that standard LLM generation is auto-regressive. What does that actually mean? It means the model generates text one single token at a time. It calculates the probability for the next word, outputs it, sticks it onto the sequence, and then runs that entire massive calculation all over again for the next word. It is a strictly sequential process. And because of that, it is an inherent, completely unavoidable bottleneck whenever you're waiting for a long, complex response.
The researchers hit the nail on the head with this quote: "As large language models scale, their inference cost increasingly dominates deployment budgets." This isn't just some abstract computer science puzzle, right? This is a massive financial hurdle. I mean, imagine paying a premium for every single syllable a 200 billion parameter model thinks up. It's creating a huge barrier to getting these models deployed out in the real enterprise world.
Moving on to Section 2, the speculation trade-off.
Now you might be wondering, what are we currently doing about this? Well, speculative decoding essentially uses a smaller, faster draft model to guess what the big model is going to say, and then the big model just double-checks it. But right now we have to choose between two imperfect methods. You've got token-level speculation. This verifies multiple drafted tokens at once, which is awesome for parallel computing, but a single wrong word ruins the whole guess. So we only get to skip a few tokens at a time. On the flip side, we have semantic-level speculation. This verifies whole logical steps or sentences, accepting much longer spans of text. Sounds great, right? But it forces the big model to verify each step sequentially, which literally reintroduces that exact same serial bottleneck we were trying to escape.
And this brilliantly illustrates that core tension. If you look at the x-axis, we have the shift from sequential to parallel verification. On the y-axis, it's the shift from short token-level spans to long semantic-level spans. Traditional autoregressive generation, stuck down on the bottom left. Spec decode gets us parallel verification, but really short spans. Spec reason gives us long spans, but we are back to sequential verification. Notice that glaring, empty top right quadrant? That is our holy grail. What we desperately need is a solution that is both highly parallel and operates over long semantic spans.
Which brings us to Section 3, introducing PARSE.
Enter PARSE. This stands for the Parallel Prefix Speculative Engine, and it is a real game changer. This framework officially achieves that holy grail of speculative decoding we just talked about. It allows a massive target model to verify long, semantic-level chunks of drafted text, but it does it entirely in parallel. It completely eliminates that sequential checking penalty that was holding all the previous semantic methods back.
The whole framework is actually built on this one really profound philosophical insight from the paper: judging is easier than answering. Think about it. The researchers proved that a massive target model can easily and confidently spot when a smaller draft model makes a semantic mistake, even if that massive model wouldn't have instantly known the perfect answer itself right off the bat. Recognizing a mistake simply takes way less compute power than generating the perfect answer from scratch.
All right, let's get into the mechanics in Section 4, how PARSE works.
So PARSE operates in three really distinct, elegant stages. You can kind of think of it like the dynamic between an eager intern and a senior boss. Stage 1 is the draft stage. The fast, small intern model writes out an entire proposed answer. Stage 2 is the verify stage. The large boss model evaluates that entire draft holistically to figure out if and exactly where things went wrong. And finally, Stage 3, the axe stage. The boss either accepts the whole thing as is or keeps the correct beginning, chops off the mistake, and seamlessly finishes writing the rest of the answer itself.
Let's ground this theory with a concrete example right from the paper. Say we ask a math question. I have a $50 dinner bill, split evenly, plus a 20% tip on the total. How much do I pay? In stage 1, our fast 8 billion parameter draft model quickly whips up a complete response. It sets up the problem beautifully, but if you look closely at step 3, it says 50 plus 10 equals 60. It makes a math error right at the very end.
Now, the absolutely crucial point is what happens next in stages 2 and 3. The massive target model looks at this draft, and it doesn't just throw the whole thing in the trash. Instead, it pinpoints the exact semantic boundary where the draft went off the rails, which is that fourth line where the math failed. It accepts all the perfectly good reasoning that happened before that point, and only spends its expensive heavy-duty compute power regenerating that final sentence to get to the correct $35 answer. To pull this off efficiently, PARSE relies on its core technical innovation, something called parallel prefix verification. Now, the big challenge here is that if the target model had to check every single sentence boundary sequentially just to find the error, well, that would take multiple expensive processing passes, which completely ruins our speedup. So the genius of PARSE is that it figures out how to evaluate every possible cutoff point simultaneously in one single forward pass.
Now, what is really interesting about this slide is how they actually achieve that single pass. They use a custom attention mask. Usually, an LLM needs a specific chat template suffix to formalize a correct or incorrect judgment. What the researchers do is cleverly append duplicated suffixes at the end of the draft. Using a visual masking matrix, each duplicated suffix only gets to see a specific chunk of the draft. The first one checks sentence 1, the second one checks up to sentence 2, and so on. So in one single computation pass, the model spits out judgments for every prefix, instantly identifying the maximum valid span. It's pretty brilliant.
Okay, let's look at the actual impact in Section 5, the speed-up results.
Diving into the hard data, the researchers used the massive Qwen-3 235 billion parameter model as their target baseline. And across the board, PARSE significantly boosts the throughput in tokens per second compared to the baseline, all while tracking the accuracy almost perfectly. But the real magic, that happens when they combine PARSE with Eagle-3, which is a token-level speculation method. When they do that, the throughput just skyrockets on complex benchmarks like Math and MMLU Pro.
In fact, on the GSM-8K math reasoning benchmark, when PARSE is composed with Eagle-3, it achieves a staggering 4.5 times speedup compared to standard generation. Think about that for a second. We are talking about getting the elite reasoning quality of a 235 billion parameter model nearly 5 times faster.
So let's quickly summarize the key takeaways from this framework. PARSE gives us roughly a 1.25 to 4.3x standalone speedup with practically zero accuracy degradation. And crucially, because it operates up at the semantic level, it is fully orthogonal to token-level methods, meaning they stack multiplicatively. PARSE shortens the total number of tokens the big model has to generate, while the token methods speed up the generation of whatever tokens are left. And honestly, the best part of the whole shebang, it requires absolutely no retraining of the models. It is purely an inference time engine.
Which leaves us with this final thought for the explainer. As large language models continue to just balloon in size, the cost of deployment is only going to become more critical. With results this dramatic that require zero model retraining, will parallel semantic verification frameworks like PARSE simply become the new default standard architecture for serving AI? It certainly looks that way. Thank you so much for joining me today. If you want to dig deeper into things like that custom attention mask matrix, I highly encourage you to check out the full RX-5 preprint. Keep learning, and I will catch you in the next one.